Okay, so today I am teaching Adam open circuit, short circuit equivalences for inductors and capacitors. And so what we have here, we have two circuits that have in common a voltage source and a resistor. Right? This circuit has an inductor and this circuit has a capacitor. Right? And so they each have a lever right here, a switch that starts off and then connects the circuit so that it is continuous. And so what we're gonna do is evaluate both of these circuits, right? The one with the inductor and the one with the capacitor, to find what the voltages are and the currents are at right away, right after we connect the switch, and a long time after we connect the switch. And the purpose of this is what capacitors and inductors do, they hold charge, right? They have to be charged like our phone batteries. Like you charge your phone battery at night and it charges up and it takes time to charge. And so these likewise take time to charge. And so there's a lot of time functions, and there's a lot of other topics that I'll have videos on of relating time to how much charge is in these branches. But for now, we're gonna figure out what it would be, what the voltage and the currents are initially, right after we switch that switch, and a long time after we switch that switch. And so Adam, I'm gonna ask you to give me some numbers, okay?
All right.
I want 1 through 10 for this. 1 through 10.
9.
9.
And
Hold on. 9 volts.
7.
7 ohms.
And
Actually, we don't even, for this type of problem, we don't even need numbers for those two, so we're not even going to include them. What? No, 1 through 10 for this one.
10 and 6.
10 volts and 6 ohms. Okay. Good numbers. Good choice. Good choices.
Glad I chose good.
Okay, so now I'm going to explain to you the inside of these boxes before I get into it all. These two rules, right, relate. These are the main differences between inductors and capacitors when you analyze circuits like these. And so what this says is that for inductors, initially, right, we're going to draw them as an open circuit, as open. And after a long period of time, we're going to draw them as short. Right? Now that's open, then short for inductors. Capacitors are short, then open. Right? So initially it's going to be short, and after a long period of time, it's going to be open. So as you can see, it's open, short, short, open. Right? There's a distinct opposite difference there. And so I'm going to do a little bit of drawing, and then I'll come back. Okay, so what I did here was I redrew what this circuit would look like initially and after a long period of time, initially, after a long period of time. The inductor would be open initially and short after a long period of time, and the capacitor would be short initially and open after a long period of time. And so first, we're going to do current, because current is easier and it's better to understand when you do the easier one first. And so current we're going to do first. So in this circuit, there is no current, right? Because it's open, right? Because it can't flow. There isn't a loop or a mesh that it can start and stop at in the same spot, that it doesn't cross this path. So this, because it's open, there is no current, and that's easy to see. And so after a long period of time in an inductor circuit, you will have a current, right? Because there is a loop, and it's related to this equation, V equals IR, which also says that I equals V over R. And so our voltage is 9 and our resistance is 7. So our current is 9 over 7. Right?
Yeah.
And so those are the currents initially over this branch. Those are the currents initially and after a long period of time. And so now we're going to talk about the voltages across this branch initially and after a long period of time. So what essentially this is ground, right? We can say whatever we want this to be, as long as it's in relationship with the rest of it. So let's just say that this node, the ground, is 0, which that's what you typically do. But this node is 0. That means this node, because of this source, is 9, right? And it crosses this resistor, so that this node is it's also 9 because of voltage division, which is in another video. But voltage division, you're going to have the specific resistor you're talking about over the total resistors, which in this case is 7 over 7, right? Times the voltage source, which is 9. So 7 over 7 times 9 is 9. So this node is 9 volts, and this node is 0. Therefore, the jump is 9. Right? So initially, this branch has a jump of 9 volts. And after a long period of time, this jump right here, right, an inductor, is the same node. So it's going to have the same voltage throughout all of it, whatever we want it to be. It's the ground. And so the voltage jump for that node is 0, or for that branch is 0. And so these, in this particular problem, all we're looking for is initial and final velocity, voltages and currents.
You don't like vectors yet?
Mixing up my statics. Okay, so now we're going to do the same thing with capacitors, except it's a little different, right? Because of the different rules we follow. And so initially it's a short, right? This branch is shorted out, and so the current, we're going to evaluate the current at that spot for the initial value, which is, right, what we said earlier, I is equal to V over R, right? So the voltage is 10, and the resistance is 6. So 10 over 6 is 5 over 3 amps, right? Which is the same as this, right? These two are essentially the same. You analyze them the same way, at least. And so for this circuit, and after, the current right here, after a long period of time, the current at this branch is obviously 0 because it's open, right? You can't have current in an open circuit. So now we can look at the voltages, the voltage jumps. The voltage jump, right? This is ground, so we can make it whatever we want. Typically, we're going to make it 0. So this entire node that entire node is 0, which means the voltage jump from here to here there is no jump. No matter what this node is, it's the same node, so it's 0. And so our voltage jump over here, right? We can't have voltage jump because they're different nodes. So this node right here, it's just like our first one. This node right here is the ground, right, all the way up to here. And we're going to say it's 0, which means this one right here is 10. Which means this one right here, just like what we proved over there with voltage division, is also 10. So this node is 10, this node is 0, which means the voltage jump is 10. And so in this particular problem, that's what we're looking for. We're looking for the initial and the final voltages and currents of our branches for inductors and capacitors. And we did it. So does that make sense?
Yep.